Hello and welcome to AUTOiNFORM online magazine. My name is Frank Massey. In this diagnostic workshop feature, I'd like to take a look at diesel particulate filters. In particular, I'd like to go through the process through which we diagnose them using the potential of one of three methods. The serial communication platform, probably the most obvious method, simple voltage with a digital multimeter, and eventually image or profile using an oscilloscope. I'm going to take them step by step because we're going to deal with the information in slightly different ways and the way in which we interpret the information in slightly different ways. First of all, why did DPFs go wrong? It's really a rather complex issue which relates to environment, the type of use the vehicle undergoes, the type of servicing or lack of servicing the vehicle undergoes, and potentially the quality of the products used, the oil, for example. DPFs essentially become blocked by the soot particles from the combustion process that the diesel engine undergoes when burning diesel fuel. So you have to take into account the functionality and efficiency of that process as a potential cause, not a symptom. The blocked DPF, of course, is a symptom. You must deal with the causes. This vehicle was presented with the usual range of DTCs, excessive soot mass content, relating to a blockage in the exhaust system, which can also be the catalyst as well as DPF, of course. In limpome, lacking power, and we began by examining the DTCs. It clearly demonstrated a potential DPF-related fault. It also had a DTC for glow plug error, and that was also dealt with as part of the repair process. We began by looking at serial data, and we took a look at this data both statically. We'll deal with these values statically and dynamically. Statically in the workshop, both at idle and when we accelerate the engine, and dynamically on the road. And the reason I've separated the two analysis is because on the road, the volume of gases through the exhaust pipe obviously increase with engine load. First of all, you've got a DTC for a DPF error. Potential, it is a blocked DPF. It could also be a faulty sensor. It could also be both. Don't fall into the trap of just changing the sensor when the DPF is blocked or changing the DPF when the sensor is also faulty. Golden rule with sensors: output, power, ground, environment, in that order. Output was wrong. We then checked the power supply, so 5-volt sensor, with a ground reference of around 200 millivolts. All of that was correct. The environment, the soot, was then potentially an issue. So first of all, we then carried out what we call a plausibility check. With the ignition key on, with the engine static, not running, you should have around 0.6, 0.7 of a volt. We'll come back to that later when we use the actual multimeter. This vehicle did have the correct voltage, around about 0.7, 0.74 key on static. With the engine at idle, it also remained at the same figure, which it should do. So initially, it didn't indicate a blocked DPF. That then led us to want to drive the vehicle dynamically on the road because the logic or the expectation then was that the DPF only became a problem at high engine load conditions when the volume of exhaust gas was such that the blockage became an issue. So we attached Autologic to the vehicle, and we're going to go through some of this data very shortly. We'll start the engine, go through some of this data. But wanted to look at the value of the calculated value from the DPF sensor, and we also connected up the multimeter at the same time. The multimeter is a very simplistic way of proving a blocked DPF, or shall we say a sensor reading error. Let's term this quite carefully. A sensor reading error is simply look at voltage, and in which case we did both. I wanted to see the correlation, the relationship between the serial data and the digital multimeter. I'm going to start the vehicle. Let's take a look at some of the values. Start the vehicle. Let's take a look at some of these values, what it was in the faulty condition and what it is now we've rectified it. Just before I do start it, I think it's fair just to go through the process through which the rectification route we took. We rectified the glow plugs. We carried out a thorough flushing procedure with the engine to clear any residual carbon, especially through the EGR valve. We then went through a manual regeneration process, which is done through the serial platform. We then re-examined the vehicle. We drove the vehicle on the road. There was no change. The DPF still suggested a blockage, so the manual regeneration was a failure. There comes a point when the blockage is such that regeneration will not work. You are then faced with one of three possibilities. You fit a brand new DPF, quite expensive. You buy an exchange DPF, or you clean it yourself. We took the third option. We chose to immerse the DPF in a chemical called Gramos. It's a branded product name. It's an aggressive decarbonizer, which engine reconditioners use to remove carbon from castings. We then, having soaked it overnight, steam cleaned the DPF in a reverse direction. Now, I'm happy to accept an argument that you should not steam them out, that steaming out may affect the substrate to such an extent that it effectively doesn't treat the carbon particles in the correct way. We had some financial restraints on this repair, and we chose that as the most sensible route. We're also interested to see if the cleaning process was effective. It turns out that it was effective. After we'd steamed the DPF out, refit it, we then did another manual regeneration process before going for a road test, before re-evaluating the data. I'm going to go through the data shortly with you, but first of all, let me start the vehicle. You've shared the experience of how we rectified the problem, and I can assure you this vehicle now is exceptional. It really is running very, very well. Full power's restored, flexible right from the bottom end, right through the speed load range, with absolutely no discharge from the exhaust at all. So it really is a very effective repair. Total cost about £800, which in relative terms is very good value for money when you consider that a new DPF alone was £800. So it's a very effective repair, and from the point of view of the independent industry, a very profitable repair in terms of time against income generated. But let me start the engine, go through some data. Right, I'd like to continue by, first of all, looking at the data relative to the DPF, which we achieve through the engine interface. We're then going to go to the particulate trap regeneration program, and I'm obviously not going to go through the regeneration process here, but what I do want to look at are these figures. Now, we have a soot particulate quantity measured in grams of 1.41 grams. That's currently the calculated level of soot with this system working efficiently. Originally, when I test drove this vehicle, this is on the road, not static, we had a maximum reading of 22 grams of soot. Now, we're still collating data. Part of our function, apart from repairing vehicles, is collating data, so we're able to intuitively know at what point systems start to go into default. So we're still collecting these figures, but we are quite confident on some of these figures and on some of these voltage readings. So we had 22 grams of soot on full load. The particulate trap sensor reading in hectopascals, now 1,000 hectopascals is 1 bar, we had around 300, 350 HPAs on the road on full load. That figure shouldn't be more than 100 at idle, statically in the workshop. As you can see now, with the process having been resolved, the problem resolved, that figure is now 10, an exceptionally good figure. So we're looking for a maximum of 100 HPAs at idle. And I would say from your observations and my observations that really you should be looking at an extremely low figure with a fully functioning and effective DPA system. So we drove the vehicle, we noted 22 grams of soot, and we had around 300-350 HPA pressure. The pressure differential sensor is a fully floating sensor. By that it has no reference to atmosphere. It measures pressure differential on the forward face, that's the engine side of the sensor where the exhaust gases are presented, and at the rear of the sensor, which is the exit route from the DPA. So it's measuring incoming pressure and exit pressure differential. And where that differential becomes excessive, it will then set a default, reducing fueling, reducing turbo boost, basically just reducing power. And until that's rectified, the vehicle will not perform correctly at all, nor, if it's excessive, will it allow manual regeneration. In which case, as was our condition, you then have to take the DPF off and replace it or clean it. So much for the serial data. Moving on to voltage. I mentioned earlier on the 4 key functions of any sensor: output, power, ground and environment. Before you blame an output error, ensure power, ground and the environment is correct. The environment in our case is soot. 2 hoses connect the DPF to the sensor. The sensor is slightly out of view at the rear of the engine on this model. During the process of cleaning the DPF, we ensured that the pipework was also steamed clear. It was actually free, it wasn't blocked. And we then conducted a plausibility test to the sensor. Now, interestingly, when we come to look at voltage with the original fault, the plausibility value, that's the key on the static value, was correct. 0.6, 0.7 of a volt. It's now at 0.58, so it has dropped about 0.1 of a volt having cleaned the DPF. But the plausibility value of the sensor was good, proving that the sensor functionality was not at fault. However, when we drove the vehicle on the road, this 0.6 of a volt went up to 4.2. Now that's an excessively high figure. The voltage went to 4.2 on full load. Full load, so far as the DPF is concerned, is achieved quite low in the torque range, around 1500 to around 2000 RPM in a low gear. You do not have to drive the engine hard to achieve full gas exit volume. The voltage went to 4.2 and instantly the vehicle went into default. Having rectified the problem, we have the same plausibility value, 0.6 at idle, 0.6 static. There is no difference in the pressure static and engine at idle. However, when we drive the vehicle now, the maximum voltage measured with a DMM is about 1.6 volts, which is an excellent figure. That's an acceptable figure, and that's on full load, dynamically measured on the road. And the figures we have from the serial data also have improved dramatically. They're now within the envelope of the correct figure. The third process I'd like to look at, having dealt with the serial communication option, the multimeter, which is really a very simple option. It's a very easy task to connect just a multimeter to the DPF sensor, drive the vehicle, and basically you want to see no more than about 1.6 volts. If you see a higher figure than that, when you get to around 2 volts, 2.5 volts, you're definitely facing a partially blocked DPF. When you get to around 3, 3.5, 4 volts, you have got a seriously blocked DPF and probably beyond the ability to manually regenerate that DPF. I am also aware of the fact that many manufacturers now have removed from their software platform the ability to manually regenerate DPFs. The main reason being, various people have managed to set the vehicle on fire. That, I think, is negligence rather than a software issue. I think they should leave the experienced technicians to do the job and leave the manual DPF regen as a feature. so that we can best decide ourselves if that is a viable procedure to go through. So there are some dangers of force regeneration. I appreciate that, but like everything, with the right preparation, the right process, I see no dangers in this at all. But as I say, some manufacturers have removed forced regeneration. The final part of the presentation really is to look at some data we're starting to gather now through an oscilloscope. We're starting to evaluate different vehicles with different types of sensor, so I'd like to show you a couple of examples. This vehicle is one of them, and a very late Hyundai is another vehicle. I'd like you to see some of these images, so what I'd like to do is just switch this off, and then we can just come back, join me again shortly with the oscilloscope, and we'll look at some visual images on the scope and deal with other ways of diagnosing DPF performance. Welcome back to the DPF presentation. So far we've looked at serial communication as an option for diagnosis. We've looked at using a digital multimeter as a very simplistic but very effective way of confirming that there's an excessive pressure generation in the vehicle. Simplistic because connection's easy, it's in real time, the numbers, the voltage is very easy to deal with. Remember, we're looking about 0.6, 0.7, key on static, with a maximum figure on the road dynamically of around 1.7 volts. Now, it's that figure I'd like to perhaps demonstrate pictorially with the use of the oscilloscope. We've seen, or starting to gather, some interesting information, patterns if you like, from this research, and what this image shows you is the voltage activity from the sensor with the engine at idle. So from the left, the engine is at idle, and we've observed from the multimeter this was about 0.6, 0.7, so let's just do a quick check. If I take a voltage reading, that measures 540 millivolts, 0.54 of a volt, excellent reading. We then increase the engine speed. Now obviously you'll appreciate that with increased engine speed you get an increase in the volume of exhaust gas, therefore the voltage, the pressure will increase, but it should not increase to a point where it forces a limp home situation. Now, I've mentioned this 1.6 volt figure. This figure keeps coming back, and it's the maximum figure I would expect to see from any DPF system in a fully functional normal operating condition. And you can see from this that the maximum voltage here is actually only 1 volt. This really is very, very good. Now this figure was taken statically, not dynamically. So I'd like to make that clear. This is a static vehicle, engine running, maximum open, wide open throttle. And we've got just over 1 volt. And then of course, when you lift off the pedal, that pressure should decay away quite quickly. It's also interesting that we start to compare this with other things. I've also compared it with air mass meters, and in this case I've used the rail pressure sensor. So if you observe this movement, you can see that there is a degree of predictability in the relationship between rail pressure, because rail pressure effectively is a means of proving what the load condition of the engine is. Rail pressure changes with load, and you can see there that the DPF is responding, or this DPF sensor is responding in a predictable manner against load. And once again, as I said, air mass meter is another good way of looking at this. So we're starting to collate this kind of data. I'd like to show you a different reading we took from the Hyundai, which I mentioned. And this is a much later system which uses a piezo sensor, which is a much more accurate means of measuring differential pressure. Here we're looking at air mass meter, rail pressure, and in particular what we're concentrating on is the green image, which is the voltage from the DPF. Now when you look at that image you would say, well, this is noise, it's interference. No, actually it isn't. If we take a look at voltage, first of all, this is a totally different vehicle, engine running at idle, and if we take a voltage reading, channel C, it's 1 volt. So this has a figure of 1 volt from the DPF sensor at idle. This is where the maximum pressure is achieved. Increase the engine speed, the exhaust gas volume increases, and when you lift off, will reach its maximum potential. That exhaust gas has to fight to get back out of the system. If we expand into this part of the image, you can see this actually is voltage, it's not noise. What you're actually seeing here, let's zoom in one more time. And this is where it gets really interesting. You can see there is a definite pattern here. You're looking at the individual turbulence within the exhaust, in other words, exhaust stroke turbulence, and also the pressure, voltage, measured from this sensor. And we're getting a range from about 1.6 volts down to about 0.6. Once again, this magical 1.6 volts is a very accurate figure, maximum figure to be achieved. But you can see that the detail in this image quite clearly demonstrates the different phases of the exhaust turbulence cycle through the sensor. So some very interesting data to be had by looking at DPF. So because this is not a new technology, but it's a problem, an industry-wide problem that we're all facing, diesels are having, I think it's fair to say, quite severe DPF problems. It will get worse because there's more vehicles now being fitted with DPFs. The drive cycle are not appropriate, a lot of short journeys, slow moving traffic. Sadly, a lot of it is down to the poor quality of oil. We need low ash oil, quality servicing, and perhaps I'm going to suggest servicing at a more regular interval, disregarding manufacturer's intervals because of the environmental issues, not because of the technical issues or specification of the particular oil or vehicle. So I hope you found this presentation of some interest in this case study of RV70. The performance has been restored totally. It's an immaculate drive now, full power restored right from the bottom end, right through the speed power range, with no discharge of emissions whatsoever from the exhaust, so a very effective repair. So we're quite pleased with the result. Total cost probably around £800, which I say is a very reasonable cost considering that a new DPF alone is £800. So in terms of offering a quality product to the customer and a good profit return, we think that's a reasonable route to undertake. If you're interested in developing your diagnostic skills, please visit the AUTOiNFORM website. If you're interested in further face-to-face training or purchase of our learning DVD modules, then please contact us through our website, and all of these features do form part of our training program. Thank you for joining me, and I look forward to seeing you in the next issue.